Hey guys, today we are talking about your new digital notebook, Nuclear Chemistry. Okay, so nuclear chemistry seems like a complicated term, but actually we use it every day, especially in our area of the country. Nuclear energy provides us with all the power that we have. So we're going to learn about how that happens, the benefits of using nuclear energy, and um, the drawbacks. So the first thing I want you to know is in this digital notebook, we've got a few different things. We can click on each title and it'll take you to the page that you need to go. But we're going to be talking about nuclear chemistry. So we're going to use this interactive diagram, which is how you can click and it'll take you to exactly the slide you need um, to see how we get radioactive isotopes, radiation, radioactive decay, and what all that means. So the first thing, if you were to click on the strong force, it would take you to this slide. This unit is going to be about nuclear chemistry, and we'll be talking about the changes in the nucleus. Remember, protons and neutrons are in the nucleus. So we're going to be talking about how protons and neutrons can get too large or be too small and how that affects radiation. So what I want you to do is pause this video and watch this video right here first. Okay, now that you've watched that video, let's talk about the strong force. Remember, you need to click on this microphone and listen to all of it first, okay? So the strong force, and thankfully the scientists didn't come up with a super complicated term. The strong force is the force that holds our nucleus together. So it's the attractive force between protons and neutrons in a nucleus and what keeps it together. So when you have a small atom like helium where there's like two protons, two neutrons, the strong force is usually really strong. It's easy to hold together two protons and two neutrons. Imagine if you're holding hands with somebody. It's a lot easier to hold hands with one person than to hold hands with 7 or 8 and walk around. So the electric force is when opposite charges attract. Protons have a positive charge, neutrons have no charge. Therefore, it makes sense that all of our positives would repel each other. So it's not very much repelling if you've just got two repelling. But imagine we're in a large atom like this. When you have a big atom with all these blue protons and all these yellow neutrons, that's a lot of repelling going on. So it's going to take a lot of force for that strong force to hold all of these together. But if our strong force is strong enough, our atom will stay fully tight together. But the big thing to notice is it's a lot easier for the strong force to hold a small atom together than a large atom. This is what makes larger atoms like uranium with 92 protons so unstable, because the strong force is not strong enough to hold it together. And so the big deal here is what happens if the strong force doesn't work? What happens if our atom is too big and it starts to fall apart? Well, if our atom starts to fall apart, that is called nuclear or radioactive decay. So when the strong force is not large enough to hold the nucleus together, it can decay, and decay means to break off or to rot off. So the unstable nuclei is called our parent isotope, and it gives off matter and energy, but once it gets too big, things start to break off. There starts to be decay, and then we have more stable atoms. So decay allows it to become more stable. It decays because it's unstable, and then after it decays, it becomes more stable. So look at this right here. Rays from the sun collide with atoms in our atmosphere, producing energy, like neutrons. And what happens is when you have air or something up here that is interacting with these neutrons, they can start to break down. So we can have nitrogen be hit by one of these neutrons and break down into carbon. And then you've got these other protons. So we've got something that's decayed. Nitrogen was there, now it's carbon and some protons. The plants, and you may think, well, that's not good. We don't want our stuff breaking down, but that makes it available for the plants. If we didn't have this type of decay with nitrogen, and remember our air is 78% nitrogen. So if we didn't have all of this, that's where we wouldn't have our carbon available for our plants. So if you're thinking we all need carbon, our air must be mostly carbon. No, our air is mostly nitrogen. But that nitrogen gets broken down into carbon because of this decay, radiocarbon decay, okay? So carbon-14 is taken by human and animals, then they excrete it, and when they excrete it, it reacts with the stuff in the dirt, and it breaks apart, and it can break apart into what's called beta decay. So a neutron leaves a proton and electron, and it has this high energy beta particle right here. Okay, and we'll learn more about that later. All right. So, in essence, radioactivity is whenever we release matter in the form of decay, and it results from a change in the nucleus. So be sure to listen to this gray part right here. Atoms with unstable nuclei are radioactive. Unstable nuclei can are caused by an imbalance in the number of protons and neutrons. Remember, when that atom gets too large and the strong force can't hold it together, there ends up being decay. So for example, uranium, this is what we use in all of our power plants around here, has 92 protons and 145 neutrons. So that's a huge atom. The strong force is trying as hard as it can to hold these together, but the repelling force is too large. So if our nucleus contains more than 83 protons, so if we're larger than atomic number 83, we're going to be radioactive, something that breaks down and decays, something that strong force is not strong enough. So radiation is when an unstable nucleus decays and the particles and energy it gives off are called radiation. So we've got three different types. We've got alpha, beta, and gamma. Okay, you can see this right here. I'll move myself up here. We've got this huge nucleus, right? Huge nucleus. Strong force is not strong enough to hold it together. So we have alpha radiation. Alpha radiation looks like this, always will. 2 protons and 2 neutrons. Think about it. Which atom has 2 protons and 2 neutrons? Helium, atomic number 2. Okay, it can release a helium atom. All right, so our nucleus is going to break down. If it releases a helium atom, 2 protons and 2 neutrons, it's released alpha radiation. If it releases only 1 electron, a high energy electron, that's called beta. And if it releases this high energy wave, that's called gamma. So there's 3 different types of radiation, and we'll talk about those in a minute.